Okay, in this video, we're going to introduce the idea of flux. We're going to use the practical situation of water harvesting to demonstrate and describe what flux is. So suppose we have a roof surface like this one, suppose we have got some rain water. So the question of interest is which quantities are going to affect the amount of water collected per time period. So we're interested in the factors that affect the rate of water collection. So the first one, of course, is going to be the intensity of the rain. So if the intensity of the rain doubles, then we expect that the rate of collection is going to double as well. For instance, right now we have got these 1, 2, 3, 4 arrows. So if we double these, then we expect that the rate of collection is going to double as well. So for instance, we now have got 8, so that is going to be the intensity of the rain. The second thing that is going to affect the rate of water collected is the angle at which the rain comes. So suppose we still have the same surface here. If the water is coming at an angle like this, then of course you can see that the amount of water, or the rate of water collection, is now going to differ. So the second thing that is going to affect the rate of collection is going to be the angle of the rain. So once you've got intensity, which talks in terms of magnitude, and angle, which talks in terms of direction, then typically this is telling us that we need to express the rain as some kind of a vector. Okay, then the other factors, of course, have got to do with the surface of collection. So I'm going to just write surface here. So with the surface, again, there is the issue of the size. So if we double the size of our surface, then the amount of rain collected is going to, or the rate of collection we expect should double. So if you take this surface and take this surface, which is perhaps twice as long as the first one, then we expect that if you keep the intensity of the rain the same, then you expect that if you've got double the surface, then the rate of collection is going to double as well. So that's going to be the size of the surface. But again, there's going to be the issue of the angle at which the surface is oriented. If you take this situation, for instance, so suppose we still have this same intensity of rain, but imagine that our surface this time is oriented like this at an angle. So you can see now that even if this surface is the same size as this one, but because of its orientation, then the amount of rain collected, or the rate of rain water collection, is going to be lower than here. So the thing that or the quantity that we use to represent the angle of a surface is the normal of the surface. So that is going to be like a vector which makes an angle of 90 degrees with the surface. So in this case, we're talking in terms of a plane surface. So it's just going to be one vector which does that. So the angle at which the surface makes with the rainwater counts. In fact, if you think of a situation where the surface is parallel to the rain water direction, then the collection literally, or the rate of water collected is going to be 0. So as this angle becomes bigger and bigger, the rate of collection becomes lower and lower. So you get the maximum collection when this vector, the normal, is parallel to the direction of the rainwater. So the quantity that becomes maximum when two vectors are parallel, or when the angle between two vectors is 0, is the cosine of theta, because cosine 0 is 1. Cosine is maximum when theta is equal to 0. So that means there's going to be direction here, or inclination. So again, when there's the direction, it means we are talking in terms of vector. So we need to express the rain in terms of a vector. We need to express the surface in terms of a vector, and then the product of those two, which involves a cosine, suggests that our flux is going to be defined in terms of the dot product. So if you call the rain vector f, for instance, if the rain is is vertically downwards, so you could imagine that f here say is 2k. So k is the vertical, but it's going to have to be negative. For this one, the normal again could be, it's going to be in terms of k, so maybe 4k, and then if you take the the dot product of these two, so that means our flux is going to be f dot the surface, which we express as a vector. So if we express it in terms of a vector, it's going to be the normal times the size of the surface. So if our vector f here is a constant, then this is the formula that is going to do it for us. So flux has got to do with, of course, things flowing. So here is the amount of rain flowing through or into the surface. Here in ordinary English, you will remember that influx has got something to do with inflow. So that is the sense in which we're using the term here. However, so this is for the case where f is a constant and the surface is a plane surface. But we could have a case where our surface is not a plane surface. So maybe our surface has got variations at points. So if our surface is something like this, then that means the normal of this surface is going to change as we change positions in this surface. And the intensity of our rain, which is the vector that we're using, could be different. So maybe the intensity is high this side and a bit weak in the middle, or weak as you go this way. And so if the intensity changes as you move in space, so then your your force here, or your which is your rain vector, is going to be a function of position. So then we can't just do this. What we need to do then is to pick a portion of the surface and the corresponding intensity at that portion, and then work out the flux, and then we add all those over the whole surface now. So the way it's going to look then is as follows. So if the surface is not plane and the intensity of the vector is not constant, so what we're going to do is take this vector at a particular position, say this one, then we are going to multiply that, take the dot product with what we're going to call ds. So this element, small element, surface element, we call ds. And then what we do is we're going to get such small surfaces, differential surface elements, or all over the surface here, and then we are going to integrate. So that means our flux is then going to be a surface integral. Now, because it's a surface, this is going to have to be a double integral. So that means our flux then is going to be defined as follows. Now remember, the surface, then we are going to express it in terms of the normal. So we're going to have the normal vector here, and then this is going to be dA, which is simply the magnitude of the differential surface element here. The n is the normal vector of each of those surfaces. So if you take this one, for instance, that could be the normal vector. But if you take an element this side, then you can see that the normal vector is now going to be pointing in a different direction to the one that we did this side. So then this becomes our formula for the flux in general, where the flux could vary and the surface could vary, of course, have a shape which is not a plane. All right. So some of the quantities that we're usually interested in the flux of is, for instance, electric field. We could be interested in the flux of an electric field through some surface or loop. We could be interested in the flux of a magnetic field, etc. Okay, so that is the sort of description or qualitative introduction to what flux is. In the next video now, we're going to look at some numerical examples given a function, a vector function, and given a surface. We're going to see how to calculate the flux of the vector field through the surface. Thank you for watching. Please do not forget to push the subscribe button and like the video. Thank you.